All right, so today we're going to be looking at another application of integration, which is finding the area or surface area of a surface of revolution. We've already dealt with volumes of solids of revolution. So when we take a region and we rotate it about some axis, we can use things like the disk or the washer or the shell methods to find the volumes of those solids. But now what we're specifically interested in is not the volume, but the surface area of these things. The derivation for this is fairly involved. It's going to take us, I think, 2 or 3 pages just to derive this result, but then we'll look at a couple of examples of applying it. So to start, we want to look at how you would find the surface area of a cone, and more specifically, just the surface area of the lateral side or the lateral face of the cone. So what we mean when we talk about the lateral area of a cone is we're talking about just this portion of it. We're not including the circular base in that area. So if we're just looking for how to find the area of the lateral face of a cone, one way of thinking about that is making a cut along this red line right here. So this red line goes from it goes along the side of this cone up to the vertex up here and down kind of perpendicularly to the base there. And the length of that cut, we're going to call that L, which represents what we call the slant height of the cone. So it's not the height of the cone. The height would be if you drop a perpendicular from this vertex down to like the center of that circular base. But the slant height goes up the side of the cone. So the length of that thing, which we're seeing here, is what we call L. If I were to cut this cone along this red dashed line and then sort of unroll that cone, we would end up with something that looks like this. You kind of unroll it, you flatten it out, and we get a sector of a circle. Okay? Now, different cones might give us different looking sectors, but if I were to take this sector now and call the angle that it makes right here theta, I could also tell you a couple of things about the other dimensions of this sector. For one thing, the red dashed line here corresponds to where the cut was made. So when we unroll it, you get either side of that cut right there. And we said that that cut has a length of L. So L now corresponds to the radius of this sector here. This blue part, so this kind of arc of the circle that we're looking at here, would have a length of 2 pi r. And the reason we know that is because if we were to roll this thing back up into this cone, that blue part is what would form the circumference of our base here. So if our base has a radius of r, the circumference of that would be 2 pi r, and now that becomes the arc length of this sector here, okay? So all these dimensions are going to help us find the area of this cone here, or the lateral area of that cone. So to do that, we're going to interpret the lateral area of this cone as the area of this sector. In geometry, you can derive a formula for the area of a sector. And before we get to that, I want to put this angle theta in terms of these other sides here. So if you measure theta in radians, then theta is equal to this arc divided by this radius. This is something you talk about when you define radians back in trigonometry. So we're not going to explain the rationale behind that, but that's kind of how radians are defined. It's this arc length divided by this radius. So that would look like 2 pi r over L. That's what theta is equal to. Now looking at the area of that sector, in geometry, we derive that sector area formula. It looks like this, 1/2 r squared theta. This is how you find the area of a sector of a circle subtended by this angle theta here. Now, since theta is up here put in terms of r and L, we can substitute this right here, okay? And I want to be careful because this r right here is referring to the radius of the sector itself in a general like a general formula. But for us, the radius of the sector is not r, it's L. So I don't want to call that R when I'm applying it to this specific sector. I want to call that L. So we would have the area of this sector, which is the lateral area of this cone, is equal to 1/2 L squared times theta. But making this substitution for theta here, I can get some cancellation with these L's. And I also get some cancellation with this 2 and this 1/2. So what I'm left with is pi RL, which is a nice, simple little formula for giving us the area of that lateral face of the cone. Okay. Now we want to go a step further with this. So this is an entire cone. We just found the lateral area. Now what I want to do is look at a truncated cone. We're going to use another word for this. We're going to call it a band. So what we're referring to when we're talking about a band is if you take a cone, not including its circular base, so just the lateral face of it, and we cut like part of it off. I'm making a horizontal cut right here to cut some amount of the tip of that cone off, and I'm left with this guy right here. So what we're referring to as a band is just the lateral face of this figure. We're not including that top or bottom circular base when we are trying to find the area. Okay, the band is just like this outside part. So I want to find the area of that band. Now, the easiest way to think of it, using the result we just came up with, is that it's the same thing as the area of this entire cone before cutting this part off, minus the cone that we cut off, because this is a cone that's missing. So we can use the lateral area formula that we found and subtract the large lateral area from the small, or minus the small one that we're removing. Okay, so what would that look like? Well, first of all, pay attention to the labels that we're using for the dimensions of this cone. So the large cone has a base radius of R2. The small cone here has a base radius of R1. The small cone has a lateral height of L1, that's what we're seeing here. And the large cone has a lateral height of L1 plus L. So this L is representing the lateral height of the band, but the entire cone that we would have started with is the sum of these two things here. So if I want the area of the large cone, using this formula that we derived up here, it's pi times R2, that's the base radius, times the lateral height, which for the large cone is L1 plus L. Then I subtract from that the lateral area of the small cone, pi R1 L1. That's using these values here. Okay, I can change the form of this by distributing this term in, combining the L1 terms that would show up here, and then factoring the L1 out, and also factoring the pi out. That's going to end up giving me an expression that looks like this: pi times, then in brackets, R2 minus R1 quantity times L1 plus R2L. Okay, so that's something that we're going to use in a moment, but now what I want to do is take a look at this picture and notice that I have similar right triangles in this diagram here. I have this large right triangle made up of the height of the large cone, the base radius of the large cone, the lateral height of the large cone, and then this smaller right triangle right here using the same dimensions from the smaller cone. They're similar right triangles because these angles are going to be equal. This angle is shared by both right triangles, and they're clearly both right triangles. So that's useful because if those are similar right triangles, I can set up their corresponding sides in proportion with one another. So we're going to do that here, okay? I'm putting the lateral height of each right triangle over its base radius, so L1 over R1. And then for the larger right triangle, we would have had L1 plus L over R2. We can cross multiply, so I'm going to get L1 times R2 there equals R1 times L1 plus R1 times L. So that's this right here, okay? Or again, if we collect some like terms, so if I subtract this term over, factor the L1 out, I would get this, okay? This gives us a substitution that we can use in the previous formula. So coming back to here, I'm seeing R2 minus R1 L1 appear in this formula, which also appears here from the proportions we just set up. So I can take that kind of larger expression and substitute R1L in for that. So that becomes R1L, okay? And if we come down here, this is what that formula would end up looking like. Now we can do a little bit more than that. I can factor an L out of this so that inside parentheses I have R1 plus R2. And then if I were to divide that by 2, so that would look like this, R1 plus R2 divided by 2, or times 1/2. I can think of this quantity as the average radius of those two cones. So going back to the diagram here, here's R1, here's R1, here's R2. If I add them together and divide by 2, I get the average of those two lengths, which is kind of like the radius that comes right through the middle here. If I were to do that, I have to compensate for the fact that I'm multiplying by a 1/2 by also multiplying this by a 2 so that those things cancel out. And then if I take that 1/2 R1 plus R2 and just relabel it as R, this whole thing simplifies down to this much simpler looking formula. So this is telling me that the area of that band that we were looking at on the previous page is equal to 2 pi times R, which is the average radius of the two base radii, times L, which is the lateral height of the band itself. Okay, this is going to be the formula that we're using to motivate what we're doing in this section. So we've been doing this for 11.5 minutes almost, and we haven't even gotten to the main thing that we're trying to do yet. Like I said, this is a pretty involved derivation. So now what we're trying to do, our goal here is to take a curve that's in the form y equals f of x. So right here, y equals f of x, some function of x. It's a curve in the xy plane. And we want to take that curve over some interval on the x-axis, a, b. So that gives us kind of a finite little snip of that curve. Then we want to rotate that curve about the x-axis, which sweeps out this surface here. This one looks kind of like a vase or something. Our goal is to find the area of this. So the way that we're going to do this, as we've already seen with a lot of these integration applications, is we start with some kind of approximation to that area. And we specifically want to choose our approximation in such a way that we can apply a limit to it somehow, which makes that approximation accurate and simultaneously turns our approximation into an integral. So the way we're going to do that is, as we typically do, take that interval AB, divide it up into subintervals, x0, x1, x1, x2, all the way through xn minus 1, xn, where that x0 is the same as A here, xn is equal to B here. And then, as we did in the previous section, I want to go to each of the endpoints of these intervals and plug those into my function to find corresponding points on the curve. So every subinterval that I created, its endpoints are going to be plugged in to give me points P0, P1, P2, all the way up through this Pn here. And also, like we did with our arc length formula in the previous video, I'm going to take each one of those consecutive pairs of points that we just plotted and connect them by line segments. So here's like what would have happened over one of those subintervals, the ith subinterval. I would have had pi minus 1 for my left endpoint, pi for my right endpoint, or these would have come from the left and right endpoints of my subinterval. And then I connect them with this little line segment right here, that red line segment. So when I rotate just this little piece of my curve about the x-axis, the area of that corresponding part of my surface is approximately going to be equal to the area I would get by just rotating that line segment about the x-axis. So it gives me a pretty close approximation, depending on how small I chose this subinterval, to just that little slice of our surface, the area specifically. But if you notice, because this is a line segment, the actual surface that it's sweeping out in red here is one of those bands that we just found an area formula for. So that's super convenient, because now I can apply the area formula that we got up here to this red band, okay? So in order to do that, the area formula requires that I know a couple of things. I need to know the average radius of the two base radii, and I need to know the lateral height. So the lateral height is actually just the length of that line segment that we drew, because this band is kind of turned sideways. So this is where L would come from. So L is equal to the length of this line segment, pi minus 1 pi. Okay, and its average base radius. So again, remember, this thing is turned on its side. The y coordinate of pi and the y coordinate of pi minus 1 are each going to give me those two different base radii. So I'm going to think of those y coordinates as yi minus 1 here and yi right here, so that the base radius is 1/2 times the sum of those two y values. Okay? So now we can plug these things into the formula that we derived up here, and I'm going to get 2 pi times r, which remember is this, times L, which is this. Okay? Next up, I want to simplify this so it's a little more usable as an integral formula. So if you remember in the previous section in 8.1, we've dealt with this already, the length of a line segment. We showed that this line segment, which remember is going to lie above this subinterval on our x-axis, we can find some number xi star in that subinterval, which when we apply the mean value theorem, ends up giving this as the length of that line segment. So this didn't just come out of nowhere. I'm borrowing the work that we did already in 8.1 when we derived our arc length formula. So that is something I can use in this formula that showed up on the previous page. Also, we know that yi minus 1 is equal to f of xi minus 1. That's where that y coordinate is coming from. It's from plugging xi minus 1 into my function. Also, you know what? I think I have a typo here. These should be yi's here. I think I just copied and pasted the same thing. Yi is the same thing as f of xi. Now, coming back to this page here, remember this xi star is some number that we would have chosen in this previous step within our subinterval xi minus 1 xi. So remember, xi minus 1 and xi are like values on the x-axis that determine this band here. We are assuming that our function y equals f of x is a differentiable formula, because or not a differentiable formula, a differentiable function. That's the word I was looking for. If that's the case, then the function's also continuous, and what that actually means in a practical sense is that if we take the endpoints of this subinterval, xi minus 1 xi, to be very, very close together, then if you pick any other value inside that subinterval and plug it into your function, you're going to get a y value that's really close to what you would have gotten by plugging either of those endpoints into your subinterval. Okay? And that comes from the idea behind continuity, where we say that a small change in x induces a small change in y, or a relatively small change. So the point of all of that discussion is that the yi minus 1 and the yi, which comes from plugging my endpoints of my subinterval into my function, are both going to be approximately f of xi star, because xi star is some number between those two endpoints, okay? And again, that follows from the fact that f is a continuous function, and we're assuming that the subinterval that we're using here is relatively small, okay? So using those things as substitutions, the sum of these two values, if I approximate them by f of xi star, then adding those together would give me 2 f of xi star, but we then divide that by 2, and so I just end up with f of xi star for this guy right here. And then we said that this length of our line segment would also be equal to this radical function, and then there's a delta x appearing there. Okay, so this is approximated well by this expression. Okay, and again, this is the area of that one red band in that diagram. Now what we need to do is take that area formula and use it on all of the bands that we would have created over all of those subintervals and add them up. So that's where this summation is going to come from. The sum from I equals 1 to n of this, where this whole expression on here represents the area of one of those bands in our approximation. As you can kind of tell from the picture on the previous page, if we can increase the number of subintervals, which makes each subinterval smaller, then this approximation is going to get better and better. So it makes sense that if we apply a limit as n goes to infinity, this is going to give us an accurate surface area for that surface of revolution. But that limit also turns this thing, because it's a Riemann sum, into a definite integral. So here we have this definite integral, and this is our formula for finding the area of a surface of revolution by taking some function y equals f of x over an interval a, b, and rotating it about the x-axis. Here it is stated again in a big red box so that you can kind of, your eye is drawn to that, okay? Same formula we can write in Leibniz notation here. So if instead of using f of x's, I prefer to use y, then I can swap this f of x out for a y. Remember, y equals f of x. That's the whole function that we started with. F prime of x becomes dy dx, and so here's a slightly different representation of that same function. This may look complicated, but there's a way of remembering it that's actually pretty helpful. So if you remember in the previous section in 8.1, we talked about the... Actually, I'm sorry, let me back this up. I wanted to talk about this first, and then we'll jump into that discussion. I was just about to start. This, again, is the surface area of a surface of revolution where we rotate a function of x, a curve given by a function of x, about the x-axis. But what if we wanted to rotate something about the y-axis? There's an alternative formula for that. So if instead we have a curve given as a function of y instead of a function of x, so x equals g of y, for example, where y is between c and d, so that's like an interval on the y-axis. If we rotate that about the y-axis, we get a very similar formula. We can follow pretty much identical steps as what we just did to arrive here. Notice the difference between this formula and this formula is instead of y, I have an x. Instead of dy dx, I have dx dy. And the limits of integration correspond to this interval instead of the interval on the x-axis. So we're basically just kind of swapping variables in this other case here. Okay, now back to what I was saying before. There is an easier way of remembering this formula. So this guy right here, this square root of 1 plus dy dx quantity squared dx, or the square root of 1 plus dx dy squared dy, either one of those represents the arc length differential. We talked about this back in 8.1. So what that means for us is that either of these large radicals, including the dx or the dy, can be swapped out for this much simpler notation, that ds right there. You just need to remember that ds represents one of those two expressions. So here is a summary of what I'm saying over there. The surface area of the first case that we look at, rotating about the x-axis, is given by this, the integral of 2 pi y ds. And if we're rotating about the y-axis, some function of y, it's the integral of 2 pi x ds. The limits of integration are left out here, but in any application, there would be limits of integration there. So this is just trying to represent those formulas in the simplest possible way for you to remember. A good way of remembering either of these formulas is to remember, for example, in the first case where we have a function of x rotated about the x-axis, the y-coordinate of any point on that curve represents the radius of a circle that you would get by taking that point and rotating it with the curve around the x-axis. That circle then would have a circumference of 2 pi y, which is exactly what your integrand is in that surface area formula. So that's one way of remembering it. Here's the case where we rotate about the y-axis. Your radius would be x in that case. So you can kind of remember these surface area formulas if you know that you're using an arc length differential here, but then you're using a circumference of either of these circles, depending on which case you're looking at, as your integrand. Okay? That's just a way of remembering. Okay, so almost 25 minutes into this video, and we finally have finished talking about the derivation of this technique. Now we need to apply it. I'm going to start my examples in the second part.